Hi guys, welcome to my channel. Today let's solve yet another Leet code question. Like, share, subscribe if you found this helpful, and let's deep dive into the description. So we were given an array books where books of I is having a thickness of I and height of I. Thickness is nothing but width of a book. Indicates the thickness and height of a book. You are also given an integer shelf width. So shelf width in the sense that we were given a shelf which is having a particular width. That's essential. We chose some of the books to place them in a shelf such that some of the thicknesses is less than or equal to shelf width, and then build the other shelf. Okay, so first, think of this that we have infinitely large height shelf with a given specific width. We need to keep the books in it, and we repeat this process until there are no books that are in place. So, and we need to maintain the order. So given the books that are given to our hand, so we need to put that in the shelf, and we need to decide on we need to keep that in the current shelf, or we need to keep a rack down the books, and we need to start a new shelf as we have infinitely long bookshelf. And this is also ways that shelf can contain the books with different heights. That would be the case, and that could be seen here, right? Because here there's a rack, and here there is a rack. Here there is a rack. We only need to check the base of the books. The base of books are correctly aligned, so the height would be the maximum height of a books that's present in the shelf, right? And we need to find the minimum height so that all the books can be arranged in the shelf. And so let's check of an example that's given over here. 1 1 2 3 2 3. Okay, great. So if 1 1 is given, then we'll keep that in the first shelf, and we need to decide on whether we need to keep the book in a new shelf, or we need to keep the book in the same shelf. Similarly, for the third also, if we have the remaining height in the first shelf, then we could keep that either at that place, or we could keep that in the new shelf. So for every book, we have either two cases. Either keep that in the current shelf, or create a new shelf for it. And this is the case for every book. So these are multiple recursive problems, right? So in the sense that if my first book is having a first shelf with remaining height, sorry, this is of index 1, and height at the very beginning would be height itself, and say shelf width would be shelf width, or height would be here 0. So if I consider moving to book 2, then book 2 can be having like it's of at index 1. It can be at the same shelf where book 1 is present. If book 1 is present, I will call this as book 1's height. And this one as book 1 books I'll call remaining width will be what? Shelf width minus books 1's width. Shelf width minus book book one's width. Now it's the same case for solving the book 2 as well. Index is 1. Now if I kept it as at new shelf, then it would be books 2 height, and same shelf width would be again shelf width minus books 2 width. But I can also keep it at the same shelf where book 1 is already present. In that case, I'll keep book 2 at same shelf 1, books 1's max of book 1's height or books 2's height, and followed by shelf width minus book 1's width minus book 2's width. So for book 3 also it would be the same. The algorithm would always be the same, except the index is being changed, and height we need to decide upon whether we are placing the book in the current shelf or in the new shelf, and width would be based on the width that's present earlier. So these are multiple sub problems that are repeating recursively. So we could think of a recursion for this, recursion calls. Uh, for also showing you how this exactly works in a graphical way, I'll show you that in editorial itself. In editorial, I found this diagram to be pretty good. So, for example, given a function, I'm assuming that this is a function that keeps the book one by taking the three parameters. So, given the same over here as well, this diagram can be checked. Recursive function is, so first it's index. Here we took height, but it's given width over here. So I'll also consider width only. So we'll align with the editorial solution. So initially at the very beginning, we'll be at index 0, and we haven't kept any book. So we'll be having remaining shelf width 4, and maximum height, because we haven't kept any book, it will be 0. Now, if I kept 1 to be at new shelf, if I kept 1 to be at new shelf, then we'll be at the first book, and the remaining height will be, first book is having height 1, width 1, so it would be 3, and maximum height would be 1. If I kept it at new shelf also, it would be the same, because new shelf and current shelf in that case would be same, because we are starting at a 0th index. Now, at this position, for keeping it book 2, we have either two choices. We can put on a new shelf, or we can keep on this current shelf. If I put on a new shelf, then uh, obviously my index would be 2, and the shelf height at that place would be 2, because my book 2 is having height 2, width 2, and followed by width as well, which is 2. If I kept it on the current shelf only, then it would be 2. And here earlier the width was 3, now it would be 1 remaining, because my current book width is 2. And height would be maximum of 1, and current width, which is 2. And similarly solving the sub problems. You can see that many sub problems here are repeating. So we can memorize this as well. But before memorizing, let's first deep dive into the recursive function, which we discussed just now. So I'll call that recursive function as helper, which is taking books, and it takes an index, it takes an width, shelf width, or probably I'll call it remaining shelf width, int height, or current, I'll call it height itself, and int shelf width. So why would I require the shelf width? Because if I in any case, if I thought of starting at a new shelf, then I couldn't use the remaining shelf width. Then I'll have all the shelf width available, because we kept a rack already till the books available, and we are moving to the next book. So here what I'll do is, I'll check if we are already to the end of a books or not. If we are already to the end of a books, then I'll return my height. Right now, case 1, what I'll do is put book in a new shelf. So if I need to keep book in a new shelf, I'll call it option 1. What I mean, how would it work is simple. I'll have height added up till now, because we need to find the minimum height that's possible. So till now, what's the height? I'm keeping a rack over there, and now I'll start with books. My index would be index plus 1, followed by, what would be the remaining shelf width, sorry. Remaining shelf width would be, I started at a new rack, so initially I would be having shelf width of it, and now I'll also take current book height and width. I'll call current book thickness is nothing but width, right? Will be equal to books of IDX 0, and current book height will be equal to books of IDX. So shelf width initially I kept a rack, so I will be having shelf width, but I kept a book over there, so it will be current book width. Got it? Why I'm taking this shelf width also passed in this helper function for the same reason. And my height would be current book height followed by shelf width. So I do have option 2 also, but option 2 can either be possible or not be possible. So I'm initializing with int max and I'm checking if my remaining shelf width is greater than or equal to my current book width. Then only I can keep the book in the same shelf. In that case, my opt2 will be I helper of books. I'll iterate to the next book and now shelf width would be remaining shelf width minus current book width followed by height would be maximum of height that's obtained till it 2 plus current book height followed by shelf width. Got this point why I'm doing this? Because if I'm having I thought to stay back at the same shelf, then I'll check all the height of maximum book that's present till it and also current book height, so that I'll keep the maximum, so that in the case we can keep a rack necessarily, so that all the books in the shelf will be accommodated. That's the example over here. And I now it's simple. I need to return the minimum of opt1, opt2. Here I'll do helper. Helper is expecting books. We'll start with index 0 at book 0. Remaining shelf width in that case would be shelf width, and height would be 0 initially, and shelf width is shelf width. There's some error over here. Shelf, acha, VIDPH. We written the same, right? Ah, while typing this, we have to. Horrible. Acha, I'm sorry for this spelling error. I'm not sure why everywhere it's doing VIDHT. It's over here. So, here as well. I'm sorry for this. But nice. So it's working fine. Mm, but n is of complexity 10 cube, and this would be raising to 2 to the power 1000, which because it would at every stage it would be having two calls, so it would be 2 per n. So we need to memorize this as well. I'm pretty sure that you might have got the intuition till here what's happening. So how my memorization works is similarly. Let's check this diagram. So can you see this out here? Like at index 1, we are also having remaining shelf width 3 that's present over 2 times. Similarly, at index 3, are having shelf width that's present over 2 times. So what I'll do is, uh, so I'll have a memo or DP vector called vector int. Uh, Let me first have the size. I'll have a DP vector with size and having a shelf. I'll use my index and remaining width that's present in the shelf to compute. So this would be shelf width, shelf width plus 1 followed by minus 1. Great. Now I'll need to pass that DP array as well into my helper function. So I'll call that DP. Got the intuition right? We check the diagram and at possibly there are multiple uh, indexes that are present with the remaining same shelf width. So in that case, I'll check if DP of my index and remaining shelf width. No need to compute them two times because we already computed them, then we'll store them in a DP array. If not equal to minus 1, then I'll return simply this. Else, here DP of would be initialized over here. DP of IDX along with remaining shelf width would be initialized over here. Where is that? Yes. So we also need to pass the DP here in the recursion calls as well. Now let's check this out if it's working fine or not. Now why do I need size plus 1 is because initially we are initializing it with shelf width and it's a zero based index array, so we need plus 1 size to accommodate all the values. I'm just checking. Yes, let me submit this out. Great, it's working fine. Uh, so to increase this complex or to reduce this complexity more, we can also use these flags. What is this telling is C plus, it's telling that I do not need the bindings from C that are required for inputting and outputting the system, so that library ingestion or headers ingestion would be reduced and our complexity or our time will be reduced fairly. I found this is being used by multiple people, so let's also try this here. So you could see the complexity is fairly increased, but I'll remove this and let me submit this out. Okay, fairly enough. So if you found this video helpful, do like this and add any comments in the comment section if you found anything is unclear. Thank you.